This is a lecture on selected topics from chapters 14 and 15 in Watson's text, Strategy and Introduction to Game Theory. So we're going to be talking about solving sequential perfect information games in extensive form. So let's start with such a game, an extensive form depiction of a game with perfect information. So in this game, there's a market leader and a market follower. This is a duopolistic market, two firms. The leader, firm A, decides whether to price high or price low, and the follower decides whether to price high or low subsequently. And so pricing high, if both firms priced high, for example, that would be synonymous with collusion. They would be working together to extract monopoly rents from the market collectively. And if they price low, they're just competing, and they're not going to earn very high profits. They aren't going to earn significant extra competitive profits. Okay, so there's some incentive to price high, but there's also incentive to kind of cheat and undercut your opponent, especially if you're following in this case. I've drawn some backwards arrows. This shows the backwards induction process of solving a game in extensive form. And so where a solution to the game is going to be a complete path from terminal to initial node. Okay, so you can already probably see that in this game, pricing low for firm A and pricing low for firm B, regardless of what firm A does, is a Nash equilibrium. And so then the outcome would be 2-2. So it would be difficult in this sequential arrangement for these firms to collude and collectively earn monopoly rents. But how do we get these backwards inductive arrows is the question. So in backwards induction, we begin from the lowest decision nodes, or that last tier of decision nodes. And in this case, the player B is making decisions at the last tier of decision nodes. And we ask, if player B were at a given node, what would player B do? Well, if player B were at that rightmost node, player B would choose to price low because 2 is greater than 1. So from that rightmost node, player B could get 2 units of payoff from pricing low, or 1 unit of payoff from pricing high. 2 is greater than 1. They would price low. So we draw arrows up from the terminal node up to the original decision node along the path that they would choose from that decision node. It's backwards induction, so we draw the arrows backwards, but we're essentially tracing the path that the player would choose from that node. And then in the left side decision node for player B, player B can get 10 units of payoff by pricing low, or 8 units of payoff by pricing high. Again, player B is receiving the second payout. At any decision node, the second payout signifies player B's payoff. So 10 is greater than 8. So from that left side decision node for player B would choose to price low. So we draw arrows up along the chosen path from that left side decision node. Okay? And you'll see that reasoning on the next slide. Yes, so on the left side decision node for player B, 10 is greater than 8, so B chooses to price low. And then we move up, because we've done all the decision nodes for player B, we move up and we say at A's single decision node, well, A knows through backwards induction that by choosing to price high, he or she will induce B to choose to price low. So if A prices high, A puts B at B's left side decision node, and then B would price low. Okay, we've already established that. Thus earning player A payoff of 1 unit. Okay, so essentially through backwards induction, A knows if A prices high, B will price low, and A will earn 1 unit of payoff. By choosing to price low initially, A will induce B to choose to price low also. Okay, we know that through our previous backwards inductive arrows. Thus earning player A payoff of 2 units. So 2 is greater than 1, so player A chooses to price low. The Nash equilibrium of this game is player A chooses to price low and player B chooses to price low regardless of what player A would do. Okay, so the outcome is 2-2. So let us consider a lender-borrower game. And so in this game, the lender can choose to lend or not lend to the potential borrower. And then the borrower can choose to repay or not repay if the funds come in. Okay, so we do this backwards inductively. We start from the last tier of the tree. And so in that last tier, B chooses between repaying and not repaying. Okay, that's the only decision node for B. The node next to that decision node is a terminal node, because if player A chooses don't lend, then player B really has no choice. The game just ends. Okay, so if player B is at their single decision node, well, they would rather have 5 than 2, so we show them as choosing don't repay under those conditions. Okay, so if the funds come to them, they're not going to repay. They would rather just keep the principal. Again, we start at B's only decision node. B can get 2 units by repaying or 5 units by keeping the principal. 5 is greater than 2, so B doesn't repay in this case. So we draw arrows along this chosen branch upwards. Okay, if A lends to B, A knows that B won't repay. In this case, leaving A with negative 5 units of payoff, the worst possible payoff for A. So if A doesn't lend, A's payoff is 0. Okay, so 0 is greater than negative 5. Therefore, A doesn't lend. A chooses don't lend. And so the Nash equilibrium is don't lend, don't repay. This may seem weird because it's not mutually consistent. Of course you don't repay if you don't lend. But what this really means is player A chooses don't lend, and player B, remember, a chosen strategy is a complete delineation of what you would do at every decision node. So player B chooses don't repay if the money comes in. Okay, so this is a contingency plan. If the money ever came in, B wouldn't repay, and that's precisely why A doesn't lend. Okay, of course maybe B says they would repay, but talk is cheap in game theory. We look at their payoffs, and in this case, which appears to be some sort of unregulated financial environment, B isn't going to repay. That's their best response. So actually the payoffs here are 0-0, and so this is a problem in a lot of developed countries, that you don't have nice regulated financial markets that encourage lending, because if you had lending with incentivized repayment, then you could get economic growth. You could get a lot of business startups. Okay, that's what the first payoff on the left, the 2-2, signifies. The lender gets a return and the borrower gets a return also. But there's such a threat in some unregulated financial environments, such a threat of no repayment, that there's either no lending going on in a region or very little going on. And so you don't have this engine of economic growth, which is small business lending and these sorts of things. But here, the Nash equilibrium, the complete path from terminal node to initial node is that player A doesn't lend. And then we also delineate that in the Nash equilibrium that player B would not repay if they did get the funding.